Hi, friends, and welcome back to our third and final lesson about kinetics. This time we're going to be talking about reaction mechanisms. So in order to talk about reaction mechanisms, we have to understand something called the collision theory, because the collision theory really explains why reactions happen in the first place. So the collision theory includes three parts. The first is that molecules have to collide. In order for a reaction to happen, two reactants have to collide in order to make products. They have to collide with the proper orientation. So if you look at the examples below, we can have collisions that happen, but if they're in the incorrect orientation, then they're just going to rebound off each other and not actually form new bonds and new products. So they have to collide in the proper orientation, but then they also have to collide with sufficient energy. So they have to have enough energy to actually form those new bonds. So break original bonds, form new bonds. And I have the picture from the video from Hitch that I showed you in class, where I like that analogy that you have to come in with the right amount of energy, but you also have the proper orientation in order to make a kiss not awkward. Okay. So speaking of reactants colliding, we can talk about how many reactants there are in a reaction or in a step of a reaction, because we're going to talk about reaction steps soon, with something called molecularity. And really, these terms are not as important as the concept behind them. So the terms are unimolecular, meaning we have one reactant, bimolecular, we have two reactants, and really you got to think about it as two molecules. Because to have two reactants, we could have two different substances, or we can have one substance, but we have two molecules of it that have to collide. And then finally, termolecular, where you would have three, and you can see the examples, two of one and then a different one, three of the same thing, or completely three whole different ones. So the concept behind it, what I want you to really get from this, almost all reactions and steps of reactions are uni or bimolecular, because the chance of three molecules colliding at the same time with the proper orientation and sufficient energy is 1/1000th of the probability of two colliding. So it is very, very rare for us to have three reactants in a step of a reaction. So something else that governs how fast reactions occur and the mechanism and by which they occur is the activation energy. So activation energy is something you've heard of before, and it's the minimum energy necessary to form a product during the collision between reactants. So consider average kinetic energy. So average kinetic energy. Not all molecules are traveling at the exact same speed with the exact same energy. So that's why we have graphs that look like this. So if this is the the whole sample, let's say, this axis shows me the number of molecules and this axis shows me the kinetic energy. So at this particular temperature, we see that there is a gradient of kinetic energies. There's various kinetic energies. Now, the majority of my molecules have this kinetic energy, but there are some that have less kinetic energy than that and some that have greater kinetic energy than that. So that's why we use average kinetic energy. So if my activation energy is much greater than the majority kinetic energy that they have, I'm only going to have very few molecules that have sufficient energy, and so my reaction is going to be very slow. If I have a lower activation energy, now I'm going to have a much greater portion of molecules with sufficient energy, so the reaction is going to happen faster. Temperature also plays a role in this. So in the previous slide, we changed the activation energy, but we kept temperature the same. This time, we're keeping the activation energy the same, but we're changing the temperature. So as we increase the temperature, because temperature is a measure of average kinetic energy, as we increase the temperature, we increase the fraction of molecules with higher kinetic energy. So at T2, I have lower average energy, and at T1, I have lower average energy than I have at T2. So what that does is it shifts our curve. So at the lower temperature, where I have a lower average, I only have this many molecules with sufficient energy. But when I increase the temperature, so I have a higher average kinetic energy, now I have a greater fraction of molecules with sufficient energy. So temperature is going to impact the rate of the reaction as well. So activation energy and temperature. And then collision theory, the fact that they have to collide, proper orientation, sufficient energy. So we can represent a reaction with what is called a reaction profile. And you've seen these before. We're going to work a lot more with them when we get to thermochemistry. But right now we just need to kind of be able to read them or interpret them. So we always have our reactants on the left-hand side and products on the right-hand side. Wherever my reactants, the amount of energy or kinetic energy that my reactants start with, to the very top of the hill is the activation energy. So that's the energy that the reactants have to overcome in order to become products. Okay? And then the change in energy, so from where I start to where I end, is called enthalpy or heat energy. And we're going to get into that in our thermodynamic unit. But at this point, just understand that that's the change in energy. So if I have less energy in my products than I started with, that's an exothermic reaction. So this particular diagram shows me exothermic. If it was endothermic, it would look like this. So just being able to read them and interpret these profiles, what they mean, and being able to identify the activation energy. If we were to talk about the reverse reaction, just know that then this would be the activation energy of the reverse reaction. Okay, so I'm going to talk for a second about something called the Arrhenius equation. And I'm going to tell you already that you will never have to do a calculation with the Arrhenius equation. Period. The end. You will not have to do a calculation with the Arrhenius equation. But in order to understand something we learn from the Arrhenius equation, we need to talk about what it is really quickly. So the Arrhenius equation relates activation energy to the rate constant. And the Arrhenius equation is that the rate constant, K, equals a constant that relates the collision theory, basically the orientation and number of collisions. Another constant, activation energy raised to the negative activation energy over ideal gas constant divided by temperature. All right, so that's a lot of stuff. Like I said, you're never going to have to plug numbers in for this. You're not going to have to do anything quantitative with this. But what this equation shows us is a couple important things. First, it shows us that the rate constant is dependent on activation energy. If I have a higher activation energy, I'm going to have a lower rate constant. And that makes sense qualitatively, because if my activation energy is really high, my reaction is going to be slower, so I have a lower rate constant. And vice versa. If I have a lower activation energy, I'm going to have a higher rate constant, because it's going to be faster. The second thing the Arrhenius equation tells us is that rate constant depends on temperature. So if you remember when I first taught you about the rate constant, I made a point to say that it is constant at constant temperature. So if you change temperature, the rate constant does change. That's why a lot of these rate questions tell you the temperature that the data was collected at, because that matters, because the rate constant is only that rate constant at that temperature. Okay, so if I have a higher temperature, then I'm going to have more collisions. My rate constant is going to increase. If I have a lower temperature, I have less collisions, and so I have a lower rate constant. It's going to decrease. So you could have a question that says, if I increase the temperature of this reaction, what will happen to the rate constant? Well, if I increase temperature, I'm going to increase the rate constant. If I decrease the temperature, I'm going to decrease the rate constant. So those are the two important things that we need to know that we get from the Arrhenius equation. You don't have to use the Arrhenius equation, you just need to understand these 2 points. The other interesting thing about the Arrhenius equation is it actually allows us to calculate the activation energy of a reaction. So if we take the Arrhenius equation and we put it into y equals mx plus b form, then we can plot the natural log of the rate constants versus 1 over the temperature, and it actually gives us a slope that's equal to negative EA over R. R is the gas constant, so that never changes. So we can use this graph to actually calculate activation energy. And I show you an example here. So we're given this reaction and we're given this data, which is rate constants at different temperatures, 5 different temperatures. And when we graph the inverse of the temperature versus the natural log of the rate constant, we get a nice linear graph, and the slope is equal to the activation energy. Now, you're not going to have to do this. It's just interesting or something to point out that we actually can mathematically determine the activation energy for a reaction from this data. But you do not have to be able to do this for the AP exam or any of my exams. So now we are getting into the main point of this last lesson, which is our reaction mechanisms. So a reaction mechanism talks about how we get from point A to point B. How do we get from the reactants to the products? And I like to analogize this, and I don't know if analogize is a word, but I use it all the time. Anyway, I like to analogize this to directions. Okay, so if you look at the map that I've given you, I mapped out the directions from Athens Drive to Crossroads Plaza. There's really 3 routes that you can take, and they're basically the same amount of time. And you've probably driven at least one of these routes a bajillion times. So when you get out, when you come out of Athens Drive, you can either turn left onto Athens, left onto Jones Franklin, right onto Dillard Drive. And that'll get you to Crossroads. Or you can turn right onto Athens Drive, turn right onto Avent Ferry, and then turn onto Tryon and go up Dillard Drive to Crossroads. Or, if you're feeling fancy, from Jones Franklin, you can get on 440 to get to Crossroads. The point of this is either way, no matter which route I take, I get from Athens Drive to Crossroads. So, what reaction mechanisms tell us is which of these routes did the reaction take? Which way did we get from Athens Drive to Crossroads? So when we're given an overall reaction, such as 2 ozone molecules react to form 3 oxygen molecules. Just at face value, looking at that reaction, I would say, okay, 2 ozone molecules collide, and now we have 3 oxygen molecules. But if we look at the reaction mechanism, we actually see that this doesn't happen all at one time. It actually happens in 2 steps. In the first step, an ozone molecule actually decomposes into an oxygen gas and a singular oxygen atom. Then that oxygen atom collides with that second ozone molecule, to form 2 additional oxygens. So this actually happens in a series of 2 steps. In the end, overall, we get an ozone, 2 ozone molecules creating 3 oxygen molecules. And we'll talk in just a second what we call this singular oxygen atom that was produced in the meantime. So reaction mechanisms are made up of individual steps called elementary reactions. So those 2 steps that we just looked at for the reaction of ozone to oxygen gas, those two steps are referred to as elementary reactions. They cannot be broken down into smaller steps. So that is like the thing that happens. There's no like, then that happens in 2 steps. Like, these are the very basic steps. And an elementary reaction has to add up to the overall reaction. So what do I mean by that? Well, if we look at these 2 steps, so step 1, step 2, or these 2 elementary reactions, I look at the left side and I'll look at the right side, so the reactant side and the product side, and I'll look to see if anything cancels. What I mean by cancel is, does it appear on the products of one side and the reactants of another step? If so, I can cancel it out. What it means is it doesn't show up in the overall net reaction. So then I'm left with 2 ozone molecules and 3 oxygens, which is in fact my overall reaction. So in a mechanism, my elementary steps will always add up to my net or my overall reaction. Okay, so let's practice canceling out parts of the mechanism so that the steps add up to the overall or the net reaction. So I look for anything that's a product in one step and a reactant in the other step, or a reactant in one step and a product in another step. So first thing I see is water, reactant here, product there, so I cancel it out. HOCl, product here, reactant here, cancel it out. HOBr, product here, reactant here, cancel it out. Hydroxide, product there, reactant there, cancel it out. So what I am left with is the hypochlorite ion, the bromine ion, a chlorine ion, and a bromate ion. So my overall reaction is ClO minus plus Br minus yields Cl minus plus BrO minus. Now I notice this is balanced on the left side and the right side, and so that is my net overall reaction. So if I gave you this reaction, you would think, oh, hypochlorite and bromine react to form chlorine and bromate. But actually, what really happens is a series of these 3 steps. So this is the mechanism for this overall reaction. Mechanisms also involve something called intermediates. So I mentioned earlier that we would talk about what we call this single oxygen atom that gets created and then used up. So an intermediate is a species in a reaction mechanism that is produced in one step but then consumed in the next step. And so what that means is it ends up canceling out and it is not included in the overall reaction. So it's called an intermediate because it's made during the reaction but then used up, and so it's not part of the overall reaction. Something else that reaction mechanisms may include are catalysts. And if you remember from biology or regular chemistry, catalysts speed up reactions by lowering the activation energy. So you can see that down here in this graph. So the uncatalyzed reaction has an activation energy of this, while the catalyzed reaction has a much smaller activation energy, and that's what allows it to go faster. So catalysts are species that are present at the beginning, but then they're also present at the end. So they get used up, but then they get reproduced. So if you remember from biology, enzymes are catalysts, and one of their characteristics is that they are reusable. So they get used, but they have to be reproduced so that they can go on and catalyze future reactions. So if we look at this decomposition of ozone again, so it's the same reaction we've been talking about, but now we're talking about the catalyzed version, because now we have something called nitrogen monoxide, which is a catalyst. So it causes the ozone to decompose faster. That's why it's an air pollutant. Okay, so we see that nitrogen monoxide is present at the beginning and then it is present at the end. But what that means is it actually cancels out and is not in the overall reaction. Something else we see here that's not in the overall reaction is nitrogen dioxide. But nitrogen dioxide isn't a catalyst, it's what we just learned about. It's an intermediate. So catalysts nor intermediates show up in a chemical overall equation, but they're parts of a mechanism or can be parts of a mechanism. Not every reaction is catalyzed, but if it has a catalyst, we'll see it at the beginning and at the end, but then it still cancels out and isn't in the overall reaction. So here's that example mechanism that we used before to practice canceling out. Well, now let's actually call the things that cancel out what they are. So water cancels out, HOBr cancels out, HOCl cancels out, and hydroxide cancels out. So water is a catalyst. It's present at the beginning and it's present at the end, but it cancels out and isn't in the overall reaction. HOCl, OH, and HOBr are all intermediates because they are created during the reaction, but then they are used up or consumed or change form. So those are all intermediates. Reaction mechanisms also have what we call the rate determining step. Sometimes can be referred to as the rate limiting step. So the rate determining step is whatever step is the slowest. So we can think about this like chain's only as strong as the weakest link. We've all probably heard that phrase before. Well, a reaction is only as fast as its slowest step. Okay? So if we look at this reaction diagram here, this is a more accurate reaction profile because it actually shows the mechanism. It shows that we have 3 steps. And our rate determining step is going to be the step with the greatest activation energy, because the higher the activation energy, the slower the reaction. So what that means for this reaction is that step 2 is my rate determining step because it is the slow step. On most questions, you'll be able to determine the slow step either from the reaction diagram and seeing which one has the highest activation energy, or you will literally just be told which step is slow and which step is fast. Finally, reaction mechanisms have a theoretical rate law. So we can take a mechanism and we can write a rate law based on that mechanism, but that rate law is only theoretical. The true rate law has to be proven experimentally, just like I told you from the beginning. That's why this whole unit, when we've been determining orders and rate laws, we've been given data because it has to be experimentally proven. Okay? But the way we write these theoretical rate laws for a reaction mechanism is we actually use the stoichiometric coefficients. So never, ever, 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 ever for an overall reaction do you use the stoichiometry to write the rate law. No, 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 no. You either have to do the initial rates method or use integrated rate laws. But for a mechanism step, an elementary reaction, we can use the coefficients. What I mean by that is if we had a reaction that was A plus 2B yields C, or excuse me, a step in a mechanism, the rate law based on this step would be A to the first B squared. I get this from the coefficients. That is the only time I can do that is for elementary reactions in a mechanism. So let's look at this example. For this one, we're told that the first step is the slow step. And since a reaction is only as fast as its slowest step, I'm going to write my theoretical rate law that comes from the mechanism from my slow step. Well, I see that there are 2 nitrogen dioxides, so my rate equals K times NO2 squared, because I could rewrite this as 2NO2. So the coefficient is 2. All right, only for an elementary reaction can I use the coefficients for the rate law. Okay, I cannot emphasize that enough. And if that is the slow step, then the overall reactions rate law, if this mechanism is correct, would match the slow step's rate law. In the last example, writing the theoretical rate law for the whole mechanism was simple because the slow step was the first step. When the slow step is the first step, we just write the rate law based on that slow step, and that is the theoretical rate law for the whole mechanism. If the slow step isn't the first step, then things get a little more tricky. So what I'm going to do is I'm going to go ahead and I'm going to write the rate law based on the slow step, which here is step 2. So rate equals K times N2 O2 times O2. Both of these coefficients are 1, so these are both first order for my theoretical rate law. Remember, we can't do that for real rate laws. Okay, immediately I see an issue. So N2O2 is an intermediate. It isn't in my overall equation, so it cannot be in my rate law. That's what causes an issue when my slow step isn't my first step. So what I have to do is I actually have to solve for that intermediate and plug in for it. So what I mean is I am going to, anytime that your slow step isn't your first step, the preceding step is going to be in equilibrium. And that just means that it's going forward and reverse. That's that double-sided arrow. What I'm going to do for that equilibrium reaction is I'm going to write the rate for the forward reaction and set it equal to the reverse. Okay? So what I mean by that is for the forward reaction, it would be K concentration of, whoops, not equal. K times concentration of NO squared because there's 2 of them. And I'm going to set it equal to the reverse. Well, the reverse would be K times N2O2. Now, I'm trying to get rid of N2O2. I need to substitute for it. So I'm going to solve this for N2O2. Well, the K rate constant for the forward and reverse are the same. So these are going to cancel out. And in this case now, I have NO second order equals N2O2. Well, now that these are equal, I've solved for it. Whoops. I can plug in the NO2 for N2O2. So I'm going to literally plug this in here. So rate equals 2O2. Now that is my theoretical rate law for the mechanism. And I can see that now what's included in my theoretical rate law are both of the reactants in my overall reaction. So I don't have any intermediates present. So for a reaction mechanism to be valid, we have to check 2 things. Does it add up to the overall reaction? And does the theoretical rate law match the experimentally determined? Because remember, the only way to know the true rate law is experimentally. So, for example, we are given this equation, and it has an experimentally determined rate law of rate equals concentration of nitrogen dioxide, first order. Then we are told that this is a proposed mechanism. We have to determine, is this a viable mechanism? So thing number 1 I have to do is I have to determine, does this mechanism add up to this overall reaction? So let's look to see if there's anything I can cancel out. Well, NO3 is present in the products as well as the reactants here, so I can cancel that out. NO2 is present here as well as here. So one of those can cancel out. So then I am left with NO2 plus CO yields NO plus CO2, which is my overall reaction. So first part, yes, it does add up. Now I have to write my rate law based on the slow step, my theoretical rate law. Well, based on this slow step, the rate law would be rate equals nitrogen dioxide second order, because there's two of them. That does not match the experimentally determined, so because they don't match, this is not a valid mechanism. Here's another example, but this time my slow step isn't my first step. So here's my overall reaction and my experimentally determined rate law. So I'm going to cancel out first to see, does this add up to my overall reaction? So I have NOBr2 is an intermediate, so that cancels out, and that's it. So I'm left with 2 NOs plus Br2 yields 2 NOBr, which is my given equation, so it does add up. Now I have to write my rate law based on the slow step. So based on the slow step, rate equals K times NOBr2 times NO. Well, we have the same issue that we had before when we said the slow step wasn't the first step, is that we have this intermediate and that can't be in my rate law. So I'm going to go to my previous one, write the rate law of the forward, and set that equal to the rate law of the reverse. These cancel out, so I have NOBr2 is equal to NO times Br2, and so I can plug that in. So rate equals K times the concentration of NOBr2 and NO. So what I did is I plugged this in for NOBr2. And now I can simplify this, and I get rate equals K times NO squared, because there are two of them, times Br. Sorry, I'm out of room. Move over a second. So I'm simplifying this. I'm putting the NO terms, so putting like terms together. And there is my theoretical rate law. Well, that matches my experimentally determined rate law, so this is a viable mechanism. All right, last example. So we're given this overall equation. Probably help if I didn't mark it out. So we're given this overall equation and this experimentally determined rate. And it's asking me which of these mechanisms, if any of them, are viable. So we're going to check first thing, does it add up? So I'm going to cancel out things that show up on both sides. So let's see, N2O4, N2, and one of these O2s. So I'm left with 2 nitrogen dioxides, 2 nitrogen monoxides, and 1 oxygen. Well, that is my overall reaction, so it does add up. Now I'm going to write my rate law based on the slow step, which is easy this time because it's the first step. I have 2 nitrogen dioxides, so it is second order. That's my experimentally determined. This mechanism is viable. Looking at the second one, let's cancel things that show up on both sides. So N2O2, this nitrogen. So I'm left with 2 nitrogen dioxides, an oxygen, and 2 nitrogen monoxides. That does add up to the overall reaction. But for this one, the rate of the slow step, the rate law would be nitrogen dioxide first order. That doesn't match the experimentally determined, so this is not a viable mechanism. Finally, for the last one, cancel out my terms. I'm left with 2 nitrogen dioxides, 2 nitrogen monoxides, and an oxygen. So this does add up to the overall reaction. But when I write my rate law based on the slow step, all of these were easy because it was the first step. that doesn't match, so this is not a viable mechanism. Thanks for tuning in, and this concludes our Unit 2 notes on kinetics.